So in this first talk, my aim is to guide you through this topic of automatic sleep scoring, trying to do that via deep learning algorithms. And yeah, we will try to answer to this very generic question, is it a problem solved? Spoiler, from a technical perspective, I will say yes, almost. Yeah, it's almost a problem solved. From a clinical perspective, my answer will be no, not at all, and we will see why in this talk. Why? So, first of all, let me introduce what is a sleep scoring. So sleep scoring is the procedure of extracting sleep cycle information over the whole night. So starting from our polysomnographic signals, specifically we have EEG, EOG, and EMG. We usually divide the whole night into windows of 30 seconds that we call sleep epochs. And then the physicians are gonna give you an answer, so are gonna score or classify the whole night into one of the 5 sleep stages. So awake, not REM 1, 2, 3, and REM. Now, what is the automatic sleep scoring? Obviously, we are trying to solve the same procedure, but we are just asking to an AI, so an AI model, a machine to solve it for us, so to solve this supervised, in this case, classification task. Now, in this talk, I'm going to focus specifically on deep learning-based algorithms. Why deep learning? Of course, you have different approaches, also shallow learning techniques, so starting from feature-based models. But why deep learning? Because in the last decade, I will say we reached really high performance. We were showing really high performance on a lot of databases, different sources too. And then also because to date, we have a huge amount of data. Indeed, here I'm just showing you the one sleep databases. This is an open access sleep databases from the National Sleep Research from Harvard. And here I'm just mentioning some of the database that we have available there. And you can see that, I mean, there are a lot of, if you have a look at the sites, just in this line, you will find up to 30K subjects coming from 16 different sleep studies. And this is really important because it's a huge source of information. It's really important to have information coming from different, I will say, data sources. When I say it's really important for the algorithm itself to learn from different data sources. So at that point, the next question will be how many automatic sleep scoring deep learning algorithms exist? Again, my answer here will be too many. I mean, from a technical perspective, we were showing in different papers, you will find in literature, really a lot of algorithms showing high performance, but I will say that different of these algorithms are always coming with some limitations. And here I just want to give you some insights. The majority of them are trained on low quality data. So data that are not enough, not heterogeneous, with noisy labels, and only few of them have been evaluated on out-of-domain data. So data coming from different labs. I want to show you that I'm able to validate my model on out-of-domain databases. Only quite recently, there have been proposed different large-scale models reaching really expert-level performance. But again, the question here is, okay, why at that point you have this huge model, why you're not using it in a clinical setting? So the next question, why? Why are the sleep physicians not using these sleep scoring algorithms? Here I want to give you 2 main reasons. The first one is related to the variability that we have on the sleep labels. That is what we call high interscore variability. You can see, I mean, one score is saying N1. They are looking at the same phenomenon. Maybe one physician is going to say to you, okay, it's N1. The other one, it's awake. The other one is N1. And of course, the majority word is N1, so the algorithm is learning N1, but on the other side, there's going to be a physician that's not going to be happy with the algorithm. Second reason, data variability. So we have data that are really heterogeneous. So it may happen that you train your algorithm on all these different data coming from different sleep labs, but you will not able to generalize on another sleep lab. So you have to learn from these heterogeneities, so meaning from different data distributions on different sleep stages. So in this talk, I'm going to try to focus and answer or give some solutions related to the first challenge and the second challenge. In the first one, I'm going to show you a possible simple solution to how to let the algorithm learn, so encode the variability of the different sleep scorings to make them all happy in a way. And the other challenge, I want to show you how the algorithm sometimes may be able to generalize on data sources that are coming from a different settings, in that case from a non-monitoring device. So let's have a look at the first one. I mean, this slide is going to be a little bit complicated, but it's just, I want to mention that in this paper, we were showing how an algorithm just exploiting a simple technique in deep learning via label smoothing and the soft consensus, we are able to encode the variability of the scores. You see in the slide, I don't know, there is no pointer. Okay. But you see in the slides that you may have, look at the same phenomenon, different scorer as saying different stuff, so awake, awaken 1 and 2. So of course you may extrapolate some probability distribution over the scores, and this is what I want to learn. This is what I want the algorithm encode. So not only what we call the one not encoded, so it's just the majority vote, so it's just awake. So to do that, we are actually inserting this information in our loss function. I'm not going to go into detail. I just want to show that in this paper, for example, we showed on different data sets scored by different sleep scores that we are actually able to reach higher performance. You see here you have different models, baseline plus label smoothing and soft consensus. You see that mainly by giving the whole information of the soft consensus with an alpha value, you reach really high performance or high performance on all the sleep stages. So if you are curious of these metrics, we can talk about that, so to go then into detail. So the results in that case were suggesting that with label smoothing along with soft consensus distribution, we can transfer this variability to the algorithm. And so this variability of the different scores are encoded in the model itself. Let's have a look at the second challenge. That is the most fascinating one from my point of view, because here we were trying to train an algorithm and transfer the knowledge of this algorithm trained on standard PSG information, so whole night information in the clinics, to another home-based device that is, in that case, a specific in-ear EEG device. So we were recording other information, but from the in-ear. So the pipeline will be like that. We are going to start from different labs, so a lot of data sources coming from different data domains, train a deep learning, so choose a deep learning algorithm and train it on these PSG, so on all these labs, so setting in a clinical domain, and then trying to direct transfer the knowledge, so no fine-tuning here. I'm going to check which kind of performance we can reach, whether we're going to use this whole amount of data, huge amount of data from the clinics. So you see here are the data that we used, open access databases, a huge amount of recordings coming from different data distributions, meaning age, so even children's we had here, for example. We choose an algorithm. This is, I will say, the state-of-the-art algorithm that you have up to date, deep learning-based approach. We will train this algorithm, so in that case, the training has been done in a three-stage setting. So meaning the algorithm was learning to discern between awake, not REM, and REM. And this metric, the F1 score, is just to give you an idea of the performance of the algorithm on the PSG, so on the training data. Not training, the test. Of course, we split it, but it's just on the same data source. And what we are going to do is to directly evaluate this algorithm on an out-of-domain database where we had in parallel information from 10 healthy subjects, whole night signals, PSG plus in-ear EEG. So it was recorded in parallel. So here I'm going to show you some results on the three-stage sleep scoring classification. You see that, of course, this is quite already amazing. It's a good results because we are showing that at that point, in another setting, we are reaching really high performance on the PSG. So we had standard electrodes, frontal, central, occipital, I would say, and you see that in all the sleep stages, we are reaching really high accuracy value. Here I'm reporting the weighted F1 score. On the other side, on the in-ear EEG setting, still, the weighted F1 score, it's high, of course, because we are waiting on the numbers of sleep stages that we had in these in-ear recordings. But you see that we were having some problems specifically on the REM sleep stage. So meaning we were really able to generalize on the awake and not REM classes, but on the REM class, we were actually failing. And there are different reasons. We can discuss about that later. But what I want to also stress here is that the algorithm, I'm sorry, I didn't mention, of course, you can see to the coins cap, another metric that, of course, you're not, because you are considering other information or even on the sleep, on the REM sleep stage, and the coins kappa is not sufficient, I would say. It's not really high as you will say on the weighted F1 score. One last thing, I want to stress that at that point, we are actually achieving with both the settings, PSG and in-ear, accuracy or performance that are on par of what the different scores were doing. So with a soft agreement. So the weighted F1 score, so on all the sleep stages, were actually on par of what the scores were doing. So going back to this is the last slide, going back to the main question, is it a problem solved? What I just want to say is, yes, from a technical perspective, we have different algorithms. We have these recently proposed large-scale algorithms reaching expert-level performance, but most interesting, the answer, so still an open problem from a clinical perspective, no. It's true that we are able to encode the variability, but these algorithms are still not reliable for the clinicians in terms of model explainability, first of all, I would say, and also uncertainty estimation, and we are working on it. Of course, there are different approaches. We can explore different approaches are out there. It's just a matter of we have to show that at a certain point, the confidence value is really important and it's something that we can rely on. Second, the algorithm, it's true that they are able to generalize on never seen data sources, but still we are not able to generalize on all the sleep stages data distribution. So one last information, what I think is that we should better define our training set, or we should better define what we mean in sleep for heterogeneity. Which kind of database it's heterogeneous enough to be then able to go on another domain and say, okay, I'm going to be able to generalize. So that's all from my side. So thanks a lot for your attention. If you have time, just please, it's lunchtime, after lunchtime, just go through these two posters that we have upstairs. Thanks a lot.